This is the screencast for section 2.3, example 7. So with all this talk about zeros and x-intercepts, did you ever think about why they actually occur? Well, the intermediate value theorem describes why zeros occur, why x values produce 0. I know, when you plug in that x value, out comes a 0. But we actually have a theorem that will predict when they happen, I guess. So this is a lot of reading. If a and b are real numbers, so two numbers on the x-axis, where a is less than b, so a is to the left of b, and if f is continuous, so we have a continuous function. So far we've got some value a and some value b. Let's see. On the interval a to b, then f takes on every value between f of a and f of b. So if I plug in a, let's say I get a point here. So we'll call this point a comma f of a. And then if I get a point b here, what if I get this point is b comma f of b? Basically what the intermediate value theorem is saying is that there will be a y value everywhere between the highest and the lowest of these two values. I can't connect these two without using up every y value in between them. I can't avoid, I have to use all of those y values in between the highest and the lowest y values. So in particular, the specific situation this is referring to, and that we usually use this for, is that if one of your y values, so let's say f of a, is negative and the other y value, f of b, is positive, reverse that. If f of a is positive and f of b is negative, somewhere in between there has to be a place where the function crosses the x-axis. There has to be a 0 in between there. So if some of your outputs are positive and some of your outputs are negative, one of them in between has to be 0, because 0 is between all positives and negatives. So example 7 says, using the intermediate value theorem, explain why a polynomial function of odd degree has at least one real 0. Okay, so there had to be a reason why they gave you odd degree in here. So I'm thinking odd degree and intermediate value theorem, positives, negatives. Well, I know odd degree polynomials have opposite end behaviors. So that means the left end behavior and the right end behavior are opposites of each other. So if I say, so the limit as x approaches negative infinity, the left end behavior, is going to be the opposite of the right end behavior. Therefore, if one of them goes to positive infinity, the other one goes to negative infinity, and vice versa. So now we can say, because polynomial functions are continuous, by the intermediate value theorem, there must be an x value c between a and b, where f of c equals 0. And this is, making a long story short, I am using the A-B scenario as described in the intermediate value theorem. Your book has a more formal way of explaining this proof. The reason why we are working on this in a more casual way is to build up, again, your knowledge of proofs. Now in example 61, it says explain why the function has at least one real 0. Well, it's by the intermediate value theorem. That is the purpose of the intermediate value theorem. But this one says explain why. Well, I'm going to say, I can actually just show examples. So let's try f of, I don't know, f of 1,000 is greater than 0, and f of negative 1,000 is less than 0. Therefore, since f of x is a polynomial, it is continuous, and by the intermediate value theorem, there exists an x value between 1,000 and, or so I'll say negative 1,000 and 1,000. We'll call it an x value c between specifically negative 1,000, 1,000. You might have chosen negative a million and a million, regardless, where f of c equals 0. So we use the intermediate value theorem in this case to explain why something has to equal 0. I didn't talk about the end behaviors of this function because I could use specific values to plug into this function. In example 7, I didn't have a specific function, so I just had to use the general description they gave, odd degree, and some characteristics I know about odd degree polynomials, in that they have opposite end behaviors to help me with my applying the intermediate value theorem.